It is a great pleasure to introduce our next speaker, Professor Jean-Marie Lehn. He is the 1987 Nobel Laureate, together with Professors Cram and Petersen, for the development and use of molecules with structure-specific interactions of high selectivity. This is the chemistry of the weak interactions among molecules, which has led to the definition of a new field in chemistry, the supramolecular chemistry. The singularity of Professor Lehn can be traced back to his high school studies in classics, where he took courses in Latin, Greek, German and English, French literature and philosophy. Actually, he got his baccalaureate, our old bachelor, in philosophy. Fortunately for chemistry, he obtained at the same time the baccalaureate in experimental sciences. He's also a musician. He plays piano and organ. And currently, he is professor at the Collège de France in Paris, although his lab is at the University Louis Pasteur in Strasbourg, where he founded the Institut de Sciences and d'Ingénierie Supramoléculaire. Professor Lehn has been the driving force in strengthening the university-industry relationships in his institute, and he hosts laboratories for belonging to some leading industries wishing to benefit from this unique academic environment. His current research covers a wide range of topics, including molecular recognition, self-assembly and mainly self-organization, supramolecular materials, and constitutional dynamic chemistry. Today, he's going to talk about steps towards complex matter, information, self-organization, and adaptation in chemical systems.
I would first like to thank Pedro Echenique, Alberto Galindo and Unai Ugalde for this fantastic meeting, organizing this, and their team, of course, their friendship and also their hospitality. I know how hospitality is in Spain, in the Basque country. It's really usually always a pleasure to come here. Now, they also provided me an occasion to get a fast training in physics. I'm a chemist. And I appreciate their open-mindedness in inviting a chemist to talk here. That gives me the opportunity to bring you through some chemistry. We heard a lot about physics. We heard some chemistry, but we will look at some more chemistry. But nevertheless, I tried to bring somewhat together what we are celebrating with some chemistry. You notice that I'm not working with IBM, so I don't have PowerPoint yet. Heini, where are you? So, three things: problem in motion, photoelectric effect, relativity. What can chemistry contribute? What has it contributed? Problem in motion, you will hear more about in the next talk. Photoelectric effect has to do with elements, metals. I'm going to see what are the relationships between chemistry and relativity, but in a very distant fashion. You may wonder what it could be. Now, let's start in a way you would perhaps not expect from a chemist to start, but it's something we expect here. Why do I show that? We heard a lot this morning about the universe. Is absolutely fantastic. When I look at this, it's so admirable what we know about. So, we started with, we think right now, the Big Bang was very hot, it's cooled down, particles formed, atoms formed, molecules formed, chemistry started. Chemistry started when it's cold enough to make molecules. But these molecules didn't just sit there. For some reason, they got together. They made more and more complicated aggregates. In some way, membranes formed, compartments formed, cells evolved, life appeared, and thinking appeared. You have already seen this morning. Rodin again. This is really, on one hand, we are crushed into modesty when we see the galaxies, the universe. But at the same time, it's incredible that the universe generated an entity which is able to think on the universe. How does this happen? How is it possible? How come from here we went here? And this can go back onto its origin. Like Pascal said, l'homme est un roseau, mais un roseau pensant. That's some French for you. Now, what happened in this evolution? From divided matter to condensed matter, to organized matter, to living matter, to thinking matter. If I want to have a generalized Darwinian interpretation, I would say the evolution has evolved under the pressure of information. Now we have to give some sense to these words. But we sort of understand. It increases. Something in the universe, not everything, but something has become more and more and more and more organized. Up to this highest level of complexity we now know is the human thought. There may be some other places where people think much better. There may be a future, in the future, some way beyond our way of thinking, but of course, very hard to imagine something beyond our way of thinking. So, let me now be a bit provocative. Albert Einstein, 1905. Quantum theory, galaxies, cosmology. Very, very important questions, but not the basic question. So we say, what is this guy, this chemist coming around and telling us that there's another question which is more basic. I claim that there's one which is more basic. How has matter become complex? In other words, how is it possible that an Albert Einstein evolved to think about and to develop relativity? How is this possible? I don't think it's more important, but it's more basic. How come the universe generated some kind of thing which was able to generate general relativity? And so I think contributing to understanding how this can have happened in small steps, modestly, because so complicated, this is what science is doing and to which chemistry is contributing. How has it happened? How has it become complex in the history of the universe? How has the biological world evolved? And if we are really Promethean, what next? Is there even something more complex than that? I have no answer to that, but we may always ask the question. Now, even worse, I even have an answer. I say, now, I hear your blood pressure going up, your pulse rate going up. No, there's an answer. Self-organization. Now, you may say, he doesn't know what self-organization is. No, I don't know. I just understand it. You can all understand what it means. Things have become organized because of the properties of matter. No intelligent design needed. Self-organization. How has this happened? Can we understand it? Can we try to understand how this happens? And we may even go a step further. And like Christian de Duve said, he wrote a book called Vital Dust. Christian de Duve got a Nobel Prize for cellular biology, some aspects of cellular biology. He wrote a book called Vital Dust. The subtitle is Life is a Cosmic Imperative. I would sort of broaden it a little and say self-organization is a cosmic imperative. In other words, my impression is you cannot avoid it. We don't want to avoid it. Now, from my readings and discussions in cosmology, discussions with Martin Rees, for instance, I understand that one can say that cosmic self-organization is a result of the action of gravitational forces on inhomogeneities in density and in speed, in expansion rates at very, very early in the history of the universe. Cosmologists here, there are plenty. They can correct me. That's what I read. That's what Martin Rees told me. And what can I do? I just have to accept it. And I'm happy to accept it because I can draw sort of a parallel saying that self-organization of living and non-living matter is a result of electromagnetic forces acting on what? On the way in which atoms get together to make molecules and the way in which molecules get together to make larger and larger entities. But this implies something else I will come to, depending on the time I have left at the end. In order to evolve, to go further, you need diversity. And diversity is randomness, and then you select on randomness. So, self-organization at the level of matter, and if I can look at it also in another way, and I mention that because Tati Hershpa is going to talk about Brownian motors. Self-organization in space, in matter, would then lead to the selection of structures, of entities, and to evolution. And self-organization in time leads to some way of taking random fluctuations and transform them into oriented motion. But we'll hear more about that, I guess, a bit later. So, this is sort of a general introduction to link what I'm telling you to the general idea of this meeting. And now, what can chemistry contribute, has contributed? We heard quite a lot about some aspects of the history of physics. Let me bring you through just a few milestones in the history of chemistry before we go a bit further. Chemistry can be defined as the science which deals with the structure of matter. Now, when I mean structure, I mean molecular matter, molecules, how they are built up, and very importantly, their transformation. This is something which personally attracted me to chemistry very much. You can take two molecules or more, you mix them together and you get something else. You transform intrinsically matter into another type of molecules, properties, materials, and so on. And this, of course, has occupied chemists, scientists, chemists all over the times. And I must cite a few people now who have contributed to the history of natural philosophy, as it was called in the times of Newton, in a very important fashion, and have made very basic contributions to science in general. One of them, and which one man who has also deals also with the universe, is somebody I must cite. And why do I cite him? Because you know, we heard this morning a lot about matter, and what I'm going to tell you about is about the matter that matters. This morning we heard that 5% of the universe is the luminous matter, the matter we know about. We are part of that. This is for us the matter that matters. This was done in the interval. So, now, what is this matter that matters? Here's the person who found out first. Or he didn't find out, but he found that it had a regularity. It was a table of elements, Mendeleev, looking very much a Dostoevsky type of hero, one of his novels. Yes, nice figure, no? And when I give a sort of a general public lecture, I always present them this, the present state of affairs, and I tell the people, you should hang this over your bed and look at it every morning. Because this is what 5% of the universe is made of. This is the table. When you look at that, you see what is in the universe. Not the dark matter, not these other things. The one I know of. So, this is a fantastic achievement. Once the bricks were found, these elements, they had to be connected, and people realized that objects, material objects, were made of these elements linked together in a given way. And they draw hieroglyphs, kind of structures. Like here, this is just a selection of some of those chemical structures which were developed in the mid-19th century. They're more or less accurate, more or less close to the ones we have now. This is by far the best one. This fellow, Loschmidt, who is not very much known, a bit in the shadow of some other big names like Kekulé, but he had the best formulas. And since you have never seen a drawing of Loschmidt, here he is. And this was a good achievement. So they knew at that time how things are connected. But it didn't have a shape yet. It was just connections. You knew that this carbon was bound to this one and so on. The next step I would like to mention, which is very important, is that to make chemistry into space, make it develop from a writing into a three-dimensional structure. This was the work of two people, Van Toff and Lebel. Let's put them side by side. Van Toff and Lebel. I would like to insist a bit on Van Toff, especially for the young people here. Van Toff wrote at the age 22 years old. This is a facsimile of his writing, of his paper. This was turned down by the journal he had to submitted it, and it was published, paid by, I was told, by his father. This is the paper which started chemistry in three-dimensional space. 1874. We heard this morning about atoms, molecules in 1905. This was 1874. And what he had in this paper was things like that, which are perfectly molecular structures. He knew, and others who were in agreement with him, that these atoms are linked, that the molecules have a structure, that have a three-dimensional structure, that it is objects called molecules, perfectly well formed from the atoms. Let me just even go a step further, and this is my last point I want to make in these historical remarks, is that there was even someone who is even more, Van Toff is not forgotten, of course. He's up there. He was the one who got the first Nobel Prize, but for something which was not this. His PhD, at 22 he published his paper, but it was not his PhD work. His PhD was something else. Not too bad. And his Nobel Prize was something else. In 1890, a German chemist, taking into account the fact that Van Toff had said the carbon is a tetrahedron, said, okay, a six-membered ring, we know cyclohexane, cannot be flat because it's 120 degrees, not 109 degrees, 28 minutes. So what happens? So this fellow did the computation, what I consider the first molecular modeling computation. It's a bad reproduction, but I just show you. This man, Saxe, he set up this geometrical relationship in the six-membered ring, solved the equations, and found what we now call the chair form and the boat form of cyclohexane, structures of cyclohexane, and many other things which were linked to that. Maybe this is also an example of how authority can have a bad influence. At that time, a very famous chemist, and rightly so, Adolf von Baeyer, had said rings are flat. So they were flat. Saxe had shown they were not. But so it was forgotten, and in 1920, another German chemist, Mohr, revived it, and so it's now called the theory of Sachse and Mohr. So, now we have come from the atom to the molecule, and we have talked us into molecular chemistry. Molecular chemistry has developed very extensively. 2 milestones, very quickly. 1, urea. 1828, Friedrich Wöhler in Germany synthesized, as we say, urea from ammonium cyanate. This was a very important step, 1828. It was also philosophically an important one, but I have no time to talk into that. Friedrich Wöhler, urea, 1828. 150 years or so later was achieved the synthesis of vitamin B12. Much, much more complicated molecule. Just illustrates how powerful this art and science of making more and more complex molecules had become. Fantastic progress in new reactions, in efficiency, in selectivity, in beauty, in the way they are put together. And since these times of the mid-70s of last century, this synthetic chemistry, building these very complex structures from scratch, that means from the elements of the periodic table, has even become more and more and more and more powerful. This achievement was the result of a collaborative work of 2 groups, one directed by Robert Burns Woodward at Harvard, and the other one by Albert Eschenmoser at the Polytechnical Institute in Zurich. I was postdoc with Woodward at that time. I made that. It's my work, but it's there. It also shows you that an enterprise like that is an enterprise which involves many, many people, and in fact it sort of costed, so to say, 120 to 150 chemist years. So, molecular chemistry, solid, mature, fantastic. What else? Then you can ask the question, is there something else we should worry about or be interested in? That doesn't look very much like chemistry, but I will convince you that it is. At least it is chemistry. The blue sphere is a tumor cell, cancer cell. The violet things are killer cells. These cells in our body are the policemen, or the policewomen. They run around, they find what doesn't work, transform cells, and their job is to kill them, to destroy them. How do the killer cells know that the other one is a cancer cell? If they make mistakes, you are in trouble. If they don't do their job, you're in trouble too. And right now, as I'm sitting here, you killer cells go around and they try to fix the thing. So, how is this possible? Another example. This rose body is a white blood cell, just has been artificially colored, of course. And the blue dots is the HIV virus. The HIV virus will find, let's say, when it collides with a white blood cell, find the ways to infect it. How does the HIV virus know that it has found the target, and how does it get in? What happens is obviously that these bodies, these cells, are complex architectures of molecules, so that when they touch, they feel each other, so to say. They recognize something. In other words, the molecules which make up the membranes, which float around in the membranes of these cells, they are the hands or the eyes of these cells, virus, and so on. In other words, we feel here, we see directly that it is a chemistry here going on which is not concerned with what happens inside the molecule, but between the molecules, when they get together, when they feel each other. I call that sometimes a molecular sociology, societies of molecules. What do? They may like each other, hate each other, repel each other, and so on. And that is what we then called supramolecular chemistry, chemistry on a level beyond the molecule, where the question arises, what happens at the level where you go beyond the molecule itself, but consider assemblies, more and more complex assemblies of molecules. Of course, this field developed very much. I don't want to go very much into details. I want just to point out some basic features. So, first thing, you have to touch. This touching is done by what we call weak interactions. For a physicist, all this is the Schrödinger equation, of course, but it's very difficult in your brain to handle the Schrödinger equation. So, it's convenient, and most of you know that, I guess, to cut up things and say that atoms in molecules are linked by strong bonds. We call that covalent. And when molecules get together and touch each other, there's sort of a glue which is non-covalent, weak bonding. Van der Waals forces were mentioned earlier by Heini Rohr. There are hydrogen bonds, there are electrostatics, all this kind of, let's say, a way in which we find it useful and easy to use to cut out interactions, to cut them up. And one of the major processes we I mentioned is the fact that molecules can recognize each other. They can selectively bind to one another. So on one hand you need interaction energy to bind. But that is not enough. You cannot be selective if you don't have information. So this recognition between cells, between a virus and a cell, between an antibody and an antigen when you get a vaccination, all the biological processes involve molecular recognition. That means molecular information. That makes me also say that chemistry is a science of matter, sure, energy, if you have to get things together, but also information. Chemical systems are informed systems. It's a science of informed matter. Now, a very simple way of representing this, something which is a nice image. Of course, like all images, it's imperfect, but it's a strong and good image, basically, is the lock and the key image of Emil Fischer. Emil Fischer, in 1894, trying to explain in simple terms how an enzyme acts on a substrate, said that they have to fit together like a lock and a key. You have the right key, it fits into the lock, and then some function, some action can develop. And Emil, that's Emil, just to show you, Emil Fischer, one of the greatest organic chemists who ever existed. Now, it was already mentioned several times, information storage by Heini Rohr also into DNA, for instance. And indeed, that is a fantastic information machine. The double helix is a long strand of information based on 4 letters, 4 chemical groups, AGTC, adenine, guanine, thymine, cytosine. So the storage of this information is in a very long sequence of these letters. This is just a small part of the human genome. It's not to make you afraid of it, but that's the way it looks. Many bases, there are millions here. And the storage is, as I said, molecular. The reading is binary system, supramolecular. These letters, AGTC, here T is replaced by uracil, but it's the simple, it's just that the thymine as a methyl group in that position. So this reading is 2323, 2 touching points, 2 hydrogen bonds on top, 3 touching points, 3 hydrogen bonds on the bottom. 2323, that's the way you read it. And that's what makes you, what makes a rat, what makes a tomato. Well, not so bad. So, chemistry can be said to be a science of informed matter, where the storage is molecular, and the processing and the reading is supramolecular. Let me just give you one example, maybe two, just brief ones, on how this then has developed. Once you recognize the problem of developing a chemistry which is not a molecular one based on strong covalent bonds, but where you try to do on the level of non-covalent bonds what has been done on the level of covalent bonds. In other words, trying now to manipulate non-covalent interactions in the way chemists in the molecular scale, molecular level, had manipulated the bonding of atoms to make molecules. Then you ask the question, okay, if we want to do that, let's see if we can develop systems for understanding molecular recognition. And as usual in science, and for instance Einstein was a master at that, you simplify to understand. And of course then you see the grand picture at the end. What means simplifying? Let's take the lock and key image of Emil Fischer. We have a lock, we have 3 keys. This is, of course, some French also for you, but easy French. The red key fits into the lock. That's the one which will be, so to say, recognized. Then you can think of a way in which you could choose first the simplest system to be recognized. And the simplest object in 3-dimensional space is, of course, a sphere. So you choose spheres in chemistry. Spheres in chemistry, one of the columns of the periodic table of Mendeleev, the alkalis, lithium, sodium, potassium, rubidium, cesium, are very important, especially also because, and that is one reason why I was interested in it, because they are part of the action potential. The functioning of a nervous system rests on the change of sodium potassium ions across neural membranes. This is what transports neural electricity. So there must be in neural membranes protein molecules able to distinguish a sodium from a potassium. And the sodium and potassium are damn close, very close. If you look at the sequence, lithium, sodium, potassium, rubidium, cesium, this has a diameter of about 2 angstroms. This is 2.5, 2.6. Very close. And again, these molecules in the nerve cell membrane, they must be able to recognize the sodium and potassium. If they make a mistake, it's a short circuit. So, can we understand that? Applying simply the lock and key idea of Fischer, at, let's say, first level, you would say, let's build a lock, which is a sphere, which has a spherical cavity, so that things can go in. And we try then to adjust the cavity size. That's indeed what one can do. This is what we did many years ago now, but just to illustrate. This small cavity is selected for lithium, the smallest sphere. You build it by synthetic methods of chemistry, a bit larger than is sodium, and a bit larger than is potassium. So you make these 3 molecules up there. If you have a mixture of sodium, potassium, rubidium, cesium, if you drop one in, it will pick up, not 100% of course, but selectively, as we say, by a certain percentage, let's say a factor of 1 to 500 or 1 to 1,000 or 1 to 10,000, that ion for which it has been built, effecting therefore the recognition of spherical objects. Very briefly, just illustrating that one can make more complicated things. A tetrahedron, that tetrahedron in chemistry of course, one of them is the ammonium ion, shown here. The ammonium ion, a nitrogen, and 4 hydrogens, looking like a tetrahedron. For that you have to build what we call a receptor unit, a binding unit, a lock, which has a tetrahedral recognition site, and that is the thing you get, where you have now also a nice illustration of what is a supramolecular entity. The outside the lock is a molecule. The inside, the key, is a molecule, but both together have new properties. This is a supramolecular, it's a supermolecule, as we call it. So this was just to illustrate what can be done, what has been done, and of course many other things have happened since then around the world. Many groups have joined in, and you may understand that one reason is obviously also if you want to develop a drug in a pharmaceutical company, for instance, a biologically active substance, you want to build a key for a given biological lock. You want to find a key which will go to that lock, inhibit it or activate it or do something to it. Now, this has developed, and I'm not going to say anything further. I want to just illustrate the basic concept. The next step would be what? And we now come back to my first remarks, these very broad remarks, where I had somewhat the head in the clouds, the head in the universe, and then we have put back our feet on the ground, looking at molecules, how they build up and so on. Let's go back now. If you want to recognize a substrate, you build the lock on purpose. You tailor-make it, as I have shown. You make a spherical cavity in a molecule to take up a spherical object of given size. You build up a receptor site, which is tetrahedral, to pick up an ammonium ion, and so on. And you make them more and more complicated. This is done by what you might call pre-organization. You pre-organize your lock for a given key. What about going from pre-organization to what you may call self-organization? In other words, let now the object you want to make build itself up, trying to understand that you don't have to make it, but you let it make itself, if you design correctly the components which are supposed to lead to it. Now, we are all self-organized entities. Let me give a simpler example than a human being, which is a bit complicated, to illustrate my point. By taking a virus, like the tobacco mosaic virus. The tobacco mosaic virus is just a bunch of molecules, nothing else. As you may know, a virus does not live. A virus is dead. It lives when it goes into a cell, but outside the cell, a virus is dead. So, the tobacco mosaic virus is a good illustration. I could have taken others, but that's the first one which was well understood, thanks to the work of Aaron Klug. And what is it made of? It's made of a shell, a tube, built from 2,200 and something, 50 sort of, bricks. This is the brick, peptides. These bricks have a surface with atoms, interactions, and this surface is self-complementary, so that one side of the brick binds to the other one, and they can bind together. It is built up in such a way that spontaneously the bricks add together, but I mean spontaneous, I don't mean random. They go spontaneously together, but in a very organized fashion, in a given way, so that they can continue to grow, to grow, to grow. So this brick at the beginning, shown here by this piece of pie, go back, go further and further and further, and build up this helix. In the middle there's a hole, and in this hole sticks the RNA, the genome of the virus. And now you have everything in place to make a discrete, finite, supramolecular, large entity. You have the bricks, the building blocks, the molecules. They get together by recognition between the building blocks, and they grow. And when the RNA in the middle is completely surrounded, the signal comes to stop. Finished. That's it. You have it. So, this is a self-organized system where you can distinguish the steps of like in a program. I like to, again, to sort of push the analogy. I don't want to push it too much, but in some ways to push the analogy with the way in which chemistry functions as an information science. The information is stored in the bricks. The bricks get together in a way which exactly corresponds to what makes them grow, and when it's finished, there is the output, the particle is finished. So you have, again, molecular storage of information, supramolecular processing, and if I want to push it even a bit further, you can even define an algorithm for processing. And we have a number of cases which I cannot get into, where when you change the way in which you read, you get another object at the end. It's quite interesting. That means the same information can lead to another object depending on how you read that information. That's something I have no time to get into. Now, self-organization. First thing, you want to design objects which will self-organize in the way you want them to get together. This is self-organization by design. You design the components, the bricks. You use a given way to get them together, hydrogen bonds, metal ion coordination, van der Waals forces, and so on. And you hope to understand progressively how this design can lead to an object of a given structure, architecture, and a given functionality. More recently, there's another aspect which has opened up, which is beyond here. I'll show you that later, if I have the time. I hope so. Let me just give you two examples of this way in which you can control self-organization. Simple ones. There are more complicated ones around, but just to give you an illustration. The first question we sort of were interested in for one of those reasons where if you ask, what's the reason we do that? Well, for fun, because you like it. No purpose of utility. This was to try to make an artificial double helix. Double helices is a mythical object. Everybody knows what a double helix is these days. And can we make double helices which have nothing to do with a natural double helix, but which have the same shape, double helical? One can, and again, I don't want to go into the details, but just believe me, if you take this molecule here, which has 3 subunits, like DNA would have 3 nucleotides, DNA, a piece of trinucleotide, 3 nucleotides. If you take this strand and treat it with a metal ion copper in the oxidation state 1, it automatically wraps up into a double helix for reasons which are perfectly well understood. And you can also make triple helices, you can make them short, you can make them long, and you can make a whole bunch of those things where the strands wrap around each other. Simply because you have designed it in the correct fashion, all you have to do, you mix it and you get it. It makes itself. To convince you that that's indeed the case, is the crystal structures which show on the left-hand side the double helix. That's the real image of the object. And this is another one, a triple helix. So, I'll come back to that in a little later. We heard in the previous talk about the possibility that maybe this self-assembly, bottom-up, may be interesting for nanoscience, nanotechnology. Let me just give you an example which illustrates that. One category of objects I've been interested in were what we call grids. Grids which are built from molecules which have binding subunits, this and this, 3 here, 4 here. And if you treat these with the correct metal ion, like iron, cobalt, nickel, zinc, they assemble spontaneously into the corresponding grid. Of course, one starts with the simplest one. Here is the simplest one, which shows a 2x2 grid. And I mentioned that, first of all, because it's the simplest to make and we studied it more extensively, and also because new physical properties are present, for instance, multiple electronic states. You can reduce, oxidize, multiple spin states, because some of the ions there are magnetic, like iron. They can undergo spin transitions, and so on. Just to illustrate this. And since we heard about STM, and we have here the person who is responsible for these developments, STM measurements on one of those grids shows indeed this is the crystal structure. This is when you do it in a given way, you can make one-dimensional lines of those grids, and at higher resolution you see the 4 cobalts which are here in this grid. This is 1, 2, 3, 4 cobalts, 4 cobalts here and there. But one can also make it much bigger, and the biggest we have made, and this is the point I would like to come to. This is a big thing with 4 sides, and here all you have to do is to take this molecule, you make it, you treat it with the metal ion, and automatically you get a grid 4x4 where 16 metal ions are nicely located at the intersection of the molecules. It's purely thermodynamics. It just means it's the most stable entity formed for reasons which have to do with lowest free energy and so on, which we could discuss if you wish, but it's not the purpose here to go into the details. You take this, you add lead, and you get this object there. What does it mean? Let's forget about all the organic stuff around and only look at the metal ions. This is what you see. You have 16 dots. The 16 dots are very close. This object is about 2 nanometers in size. It makes itself, don't have to make it. Maybe someday we'll be able to address it. We have now ways also to introduce at given positions a given ion different from another one. But I want to say here is not that we are going to change the way you make chips in the next years. But just to point out that the ability of molecules to do much more than let it having to be constructed, but to construct themselves into complicated architectures opens a possibility, which is that by programmed self-organization, you may access very complex architectures. And this may be an alternative or a complement to what is fabrication. And when I mean fabrication, I also mean bottom-up fabrication. It's not because here, bottom-up fabrication can be imagined. You can synthesize things which are bigger and bigger and you can fabricate. But here it's bottom-up self-organization. And as also Heini pointed out at the end of his lecture, the goal is not to make things smaller and smaller. The goal is to make them more complex. Forget about the size. Feynman said there's a lot of room at the bottom, of course, but I claim there's much more room on the top. Simply because of making them smaller makes it possible to compress more and more and more components into a given volume. But the purpose is to make it more complex. And the best computer around for the moment is still the brain. That's self-organized, and the components are not nano. So, self-organization may help to achieve self-fabrication rather than having to fabricate. Self-connection and not having to address. We are self-connected. I talk to you, you hear me. I see you, you see me. We are self-connected. Self-repairing, yeah. If your thing is not correct, Boltzmann will tell you that you look at your hypersurface until you find the best stage. Adaptation, we'll see that in a moment what that means. The system may be also able to adapt to changes in the conditions. And of course, rather than make things smaller, make them more complex. This is just to point out that the approaches to nanoscience and nanotechnology, of course, are extremely powerful. There's one approach on the interface with physics where you fabricate, you manipulate, you set up, you connect. There's another interface which is inspired by the way biological objects put themselves together. There's nothing mysterious. When I say biology, I don't mean by that there's something mysterious. It's just the most complex world of molecules we know about. And we can learn from that because we are part of it. And so this builds on self-organization and on adaptation to make more and more complex forms of matter. Now, the last point I want to come to deals with another property which also sort of came out of supramolecular chemistry and was linked to a feature which at the beginning was not so important because the beginnings were recognition, selectivity, building up structures, self-organization on the basis of recognition and so on. But then, and I'll show you this experiment, it's a lot of chemistry, but okay, why not? I had shown you earlier that by making these 4 molecules on the left and treating them with what you needed to wrap them up into double helix, they do form a double helix. Then we did something which is something terrible for chemists. We spend our time trying to make clean compounds, pure compounds. So we mix them. But then you can ask an interesting question. We mix it, we put it in the same conditions, question, what is it going to do? Will it randomly give any kind of combination? Or will it find out the correct pairing? Now, for thermodynamic reasons, it finds out the correct pairing as shown here. But the feature I want to point out here, why can it do it? Because it's dynamic. In other words, it can search. It has a search procedure. They get together, and when you look at this by fast methods, you see that at the beginning, all these things don't know what to do really. They look around. I'm a bit too anthropomorphic here, but that's so more or less what happens. They look around, and they finally, you see the spectral data and so on, get sharper and sharper and sharper. In the end, you have the right compounds. In other words, it is because the architecture can dissociate, reassemble, and explore the hypersurface that you end up with the correct pairing, because the instructions are robust enough to resist the fact that they're not pure anymore, but they are mixed. So this means that dynamic chemistry has another feature which is usually, until rather recently, was not sort of considered to be part of dynamic chemistry. The most easy, the most simple way, the way in which one looks at dynamic chemistry, the traditional one, is dynamic chemistry is a reaction dynamics. Rightly so, that's correct, that's of course the basis. There are also motions, and we will hear more about that shortly. Motions in molecules. Molecules have internal motions, they have overall motions. But there's another dynamics which is constitutional. I mean by that, this is dynamics which deals with the fact that the molecular or the supramolecular objects you deal with can fall apart and reassemble, reshuffle their components, incorporate some, decorporate others. And you can indeed show that this is the case. And you can also transfer that onto the molecular level. The molecular level meaning that you go from bonds which are non-covalent and weak to bonds which are covalent and strong, but which can be broken and reformed, and which do that spontaneously. There are classes of these kind of bondings. So these are constitutional dynamics which give you the possibility to have a reversibility, because on one hand the lability of non-covalent interactions makes it possible at the supramolecular level, and on the molecular level you have to introduce intentionally bonds which can break. This means that you generate diversity. And diversity is absolutely fundamental if you want to evolve. There's no finalism, no intelligent design. You just make a lot of things. And the one which is better, that's the one which will stick. Darwinian. Then you can select components. So, this means, indeed, I can now open this, self-organization by selection. Making systems where the self-organizing object can select out of the surrounding what it needs to build itself up. And this can be done. We have some simple cases for the moment, but it does function. So, selection versus design. Of course, design is fundamental. You want to understand how to do things. Pre-organization relies on design. You pre-organize for a given purpose. Self-organization can, on one hand, be directed by design, but it can also, because it has these features of reversibility, perform selection. This is a sort of a way of introducing a sort of a Darwinistic point of view into the way in which chemistry is developing. Now, we can then set up what we call libraries of dynamically interconnected components. What do I mean by that? I want to illustrate that simply by the lock and key, because that gives a sort of a good image. And let me just give the following illustration using drug design. When you want to make a molecule a drug for a given biological action, as I said, you try to make a key for a given lock. More recently, people have come around to do what they call combinatorial chemistry, where they recombine bricks to make different molecules, saying that if you make enough of them, one of them will fit. You don't need to design, you just try, you screen. The other way, and this is what I think is perhaps interesting in this general idea of constitutionally dynamic chemistry, is to make pieces of keys. If you have here a lock, and you have pieces of the keys, not the keys, but you must have pieces which can stick together and reshuffle themselves, so as to generate all the virtually accessible space of all keys. They don't need to be there, they just need to be accessible. If then you drop in your block, and if one of those dynamically exchanging assemblies fits better than the other, that's the one which will fit and will be hopefully amplified or at least detectable. So this is this way in which one can develop a dynamic chemistry which deals with constitutions, and where one can therefore introduce into chemistry this dynamic way of looking at the constitution, which is a bit shocking for chemists at the beginning, because we usually like to deal with molecules which are stable, and they are not stable. You put them in the fridge to cool them down, to say, okay, don't decompose. Here, intentionally, you make systems which are able to reshuffle, to generate new properties, and which will then react to the environment. When I mean react to the environment, I mean by that simply, for instance, by changing the pH, for instance, you will protonate some pieces and not the others, and you change. In fact, I discussed a little bit with Anton Zeilinger. You know, when I think about that, of course, it has nothing to do with quantum entanglement. Nothing. But it's an entangled system. In that what, if you change something, one component in these mixtures, all the others will be changed, because they feel that you have changed one, or they feel. They readjust the whole thing. They will all the time readjust, you perturb in some way. So it's a highly cross-connected system. And this allows then the system to be able to adapt by selecting what is needed through this dynamic exchange modifications of constitution. So, to conclude, self-organization, on one hand, is for me the most, as a chemist, the most exciting problem where chemistry can contribute to, trying to modestly, progressively build up systems which we can understand, we can control, and we hope also will contribute to the understanding of how biological self-organization occurs. And I insist on the fact that for me biological self-organization is based on molecules, obviously, like I guess for most of you. So we want to describe the processes which can lead to these more and more complex forms of matter, understand them. Describe is the first thing. Then you try to understand, and maybe, if we understand well enough, we will be able to create new expressions of that. The final remark I would like to make has to do with 2 points. One, it was said this morning that chemistry is the science of the 19th century, physics the science of the 20th century. Some people say biology of the 21st. I leave it to physicists, to biologists to agree or to disagree with this. I would say that chemistry is the science of the 25th century. Simply because there's still so much to understand. We have in front of us biological matter, which reveals how complex it can be, which we are trying to understand. And we know that the basic principles of this, we more or less have them. The physicists have given us the basic principles. But knowing the basic principle is not knowing exactly how the system functions. It's the same thing as you can know the rules of painting, but that doesn't make you a Picasso. And since we spoke about art, I finish with this. Art is, of course, one of those things in human culture which is all physically well understood. But that doesn't make a Mozart quintet. It still sounds. So, I mean, there's the things which are depending on features which are totally predictable once you have it. But there's no necessity to have this exact arrangement of sounds. In that respect, chemistry opens, and this is one reason for me to be a chemist. Of course, I would like to be a physicist, a mathematician, whatever. And to be a chemist, which is the possibility to be able to express out of the elements which the universe gives to us all the possible combinations which don't exist yet. Like Rodin out of a stone makes the thinker. The stone doesn't contain the thinker. The table of the periodic table elements doesn't contain what we can do with it. So, it's our purpose. And to finish with somebody, David Hilbert, on his grave, has this sentence, wir müssen wissen, wir werden wissen. We must know, we will know. I think that's a statement for us scientists, and I think, personally, I think we will know. There's dark matter, we don't know yet what it is, Raphael, but I think we will know. Thank you very much.